Hi students, in this lecture I will discuss Hund's rule, Pauli's exclusion principle, orbital-wise electronic configuration of atom and ion, calculation of magnetic moment, dia and para nature of species, unit of magnetic moment, and calculation based on Hund's rule and Pauli's exclusion principle. Clear? Listen. Let's start. What is Hund's rule? Hund's rule is only applicable for degenerate orbitals. I am repeating, Hund's rule is only applicable for degenerate orbitals. And degenerate orbital means the orbitals which has equal energy. And we know that all 3p orbitals having equal energy and all 3p orbitals commonly known as degenerate orbitals. Any p, 2p has 3 orbitals, px, py, pz, and all have equal energy, and hence p has 3-fold degeneracy, commonly known as degenerate orbitals. Similarly, d has 5 orbitals, all 5 orbitals having equal energy, commonly known as degenerate orbitals. Similarly, all 7f orbitals having same energy, commonly known as degenerate orbitals. Now, Hund's rule is in degenerate orbitals, electron will be filled in such a way as to give maximum spin multiplicity. I am repeating, in degenerate orbitals, electrons will be filled in such a way as to give maximum spin multiplicity. Look at board. Topic is Hund's rule in degenerate orbitals. And degenerate means having equal energy. Electrons will be filled in such a way as to give maximum multiplicity. And spin multiplicity formula is equal to 2s plus 1, where s is total spin of electrons in degenerate orbitals. S is total spin of electrons in degenerate orbitals. I am repeating, in degenerate orbitals, electrons will be filled in such a way as to give maximum spin multiplicity. And spin multiplicity is equal to 2s plus 1. That is, 2s plus 1 value will be maximum, process will be correct according to Hund's rule. Clear? And where s is total spin. Example. Look at board. Example D5. We know that D has 5 orbitals. All 5 orbitals having equal energy. According to Hund's rule, listen, 5, 1, 2, 1, 2, 1. If one student filled 5 electrons this type, then What will be a spin multiplicity? 2s plus 1. S is total spin. Listen. Plus half minus half 0. Plus half minus half 0. Plus half. The 2 into total spin. Plus half plus 1. 2 and 2 cancel. 2 and 2 cancel. And after calculation, it will be 2. Now, second student filled all 5 electrons in such way. And plus half, minus half, plus half, minus half, plus half, minus half, 0, plus half, minus half, 0, plus half, and hence a spin multiplicity 2 into total spin half plus 1, it will be 2. Next, other student, third student, filled all 5 electrons in d orbital in such a way. Plus half, plus half, plus half, plus half, plus half, 1. Plus half 3 by 2, plus half 2, and again minus half. That means plus minus 0, 3 by 2. 2 into 3 by 2 plus 1, 2, 2 cancel. And after calculation, it will be 4. And fourth student, plus half, plus half, plus half, plus half, plus half. After calculation, total spin will be 5 by 2, plus half, plus half, plus half, plus half, and 2 into 5 by 2 plus 1, half cancel, it will be 6. Clear? Clear? Now, total spin is equal to 5 by 2. Spin multiplicity is equal to 6. And in all 4 options, it is maximum, and for 5 electron, spin multiplicity is equal to 6 will be highest. And hence, option number A, process 1 wrong, process 2 wrong, C number wrong, only D number is correct. According to Hund's rule, only 4th number option, D number option is correct, because in this process, in this way, spin multiplicity maximum. Again, second example, D4. What will be maximum spin multiplicity and which is correct process, which is correct way according to Hund's rule? Look at about D4. That means D has 4 electrons, and we know that D has 5 degenerate orbitals. Orbital 5, but electron 4, 1, 1, 1, 1. Plus half, plus half, plus half, plus half. That means 4 by 2. 2 into 4 by t. It will be 5. Again, from right to left, plus half, plus half, plus half, plus half. But a spin value plus half for 1 unpaired electron, and for 4 electron, it will be 4 by 2. And after calculation, it will be also 5. Again, plus half, plus half, plus half, plus half. That means 2 into 4 by 2 plus 1. Listen, when single electron in an orbital, either upward or downward, either clockwise or anti-clockwise, then first spin normally plus half. And hence plus half, plus half, plus half, and total spin 4 by 2, spin multiplicity 2 into 4 by 2 plus 1, 5. Again, plus half, plus half, plus half, plus half, 2 into 4 by 2 plus 1, 5. And hence, listen carefully, according to Hund's rule, all are correct. Clear? Never confuse. According to Hund's rule, all are correct. All are correct. But normally, we will take wave first, option number first. But according to Hund's rule, because in Hund's rule, it is written, electron enters in such a way as to give a spin multiplicity. Electron will be filled in such a way as to give a maximum spin multiplicity, and in all 4 options, maximum spin multiplicity, and hence According to Hund's rule, D4 written as all 4 types and all are correct. Clear? Hund's rule, I am repeating. In the degenerate orbitals, electron enters in such a way as to give maximum spin multiplicity. In other statement, in the degenerate orbitals, electrons will be filled in such a way as to give maximum spin multiplicity. Clear? Listen. Conclusion of Hund's rule. Conclusion. And conclusion is in degenerate orbitals, maximum number of unpaired electrons in same spin. Listen, maximum unpaired in same spin gives maximum spin multiplicity. I am repeating. In degenerate orbitals, maximum unpaired, but not only maximum unpaired in same spin. Look at board. Maximum unpaired in same spin. Maximum number of unpaired in same spin gives maximum spin multiplicity. How to obtain maximum of spin multiplicity? Maximum unpaired in same spin. Maximum unpaired in same spin. Now, one question. Which of the following orbital diagram of D3 is oblique are correct according to Hund's rule? According to Hund's rule, which of the following orbital diagram is correct? Listen, D has 3 electrons, and we know that D has 5 degenerate orbitals. There are 5 orbitals, all are degenerate. 3 electrons, 1, 2, 3. There are 3 unpaired. In 3 electrons, all 3 unpaired, and all have same spin, and hence option number first correct. Now option number B. In option number B, listen, there are 5 orbitals, but 3 electrons, 1, 2, 3, and all have same spin, and hence, according to Hund's rule, B is also correct. But in C number, there are 3 unpaired. Unpaired in A, B and C, D. In A, B, C, all have 3 unpaired. But in A, B, electron spin same. But in C option, electron spin different. And hence C number wrong. And in D number, there are less unpaired. And hence D number also wrong. And hence Hund's rule is maximum unpaired in same spin gives maximum spin multiplicity. Now, conclusion of Hund's rule. Listen, logical statement of Hund's rule. Logical statement of Hund's rule. Listen carefully. Logical statement. In degenerate orbitals, electron will be filled one by one in same spin. First time. I am repeating. Logical statement. In degenerate orbitals, first time electrons will be filled one by one in same spin. And second time electron will be filled one by one in opposite spin. Look at both. In degenerate orbitals, first time electrons will be filled one by one in same spin, and second time electrons will be filled one by one in opposite spin. Look at board. Listen, if D has 8 electrons, and we know that D has 5 orbitals. How to fill all 8 electrons in degenerate orbitals of D? We have 8 electrons, and according to Hund rule, filled one by one. 1 electron, 1 electron, 1 electron, 1 electron, 1 electron. First time, one by one in same spin. Now, second time, when electron filled second time, then one by one in opposite spin, and hence opposite spin, opposite spin, opposite. And it is correct according to Hund's law. Again I am repeating, when D10, we know that D has 5 orbitals, first time 1, 1, 1, and second time 1 by 1 with opposite spin, and according to Hund's rule, it is correct. Clear? Now, next, orbital wise electronic configuration. Look at board. Chromium atomic number 24, yes or no? And 24, that means argon, inert gas, nearest inert gas, and for chromium normally 4s2 3d4, but it is wrong because half filled d orbital more stable, and hence 4s 1 electron transferred to 3d, and hence correct answer is 4s1 3d5 due to half fill, a stable half fill of d orbital. 1 electron exchange to d5, 4s electron transferred to d5 for half fill. Now manganese, argon 4s2 and 3d5. But listen, in orbital diagram, S has only 1 orbital, 1 electron. D has 5 orbitals and 5 electrons, and hence 1, 1, 1, 1, 1. S has 1 orbital, 2 electrons, opposite spin. And D has 5 orbitals, 5 electrons. First time 1, 1, 1. Clear? Now, iron, argon, 4s, 2, 3d, 6, and d6, that is 1 electron, 1 electron, 1 electron, 1, 1, 5, and last 6 electrons. Now, iron has 2 plus ferrous ion. That means when iron atom remove 2 electrons, when iron atom lose 2 electrons, then it forms ferrous. And always keep in mind, electron always remove from last orbit. I am repeating, electron always remove from last orbit. Listen, in case of iron, last electron filled in 3d orbital, but during removal, electron do not remove from 3d, it remove from last orbit. 3d, that means orbit number 3rd, 4s orbit number 4th, and hence 2 electron remove from 4s orbit, and hence argon, and 2 electrons remove, that means 4s 0 and 3d 6. 1, 2, 3, 4, 5, 6. Now, iron 3 plus, and iron 3 plus means when it remove, iron plus plus remove 1 more electron. 1 more, that means remove from 3d, and hence now argon and 3d 5, 1, 1, 1, 1, and 1. Clear? Look at board. In iron atom, there are 4 unpaired electrons. 4 unpaired, because 3d has 6, 4 unpaired. In iron plus plus, 4 unpaired, because 2 electrons removed from 4s. And in iron 3 plus, there are 5 unpaired electrons, and 5 unpaired means, listen, 5 unpaired electrons means, listen carefully, 1, 2, 3, 4, 5. Iron 3 plus has 5 unpaired. Clear? Now, next topic is Pauli's exclusion principle. Look at board. Pauli exclusion. And Pauli's exclusion principle is, listen carefully, all four quantum numbers of two electrons of an atom never equal. I am repeating. All four quantum numbers of two electrons of an atom never be equal. In an atom, two electrons having different value of all four quantum numbers. That means all four never be equal for two electrons of an atom. Maximum three quantum numbers may be equal. Not necessarily all three equal. Maybe three quantum numbers equal, maybe two quantum numbers equal, maybe one quantum number equal. All four may be different, but all four never equal. All four may be different. All three may be same, may be different, but all four quantum numbers never equal. Look at board. All four quantum numbers of two electrons of an atom never equal. Example, if 1s, 1s2, one electron, one electron. In 1s, for both electron, principal quantum number 1. First quantum number same. In s suborbit, azimuthal quantum number always 0, and hence for both electron azimuthal 0 same, principal same, azimuthal. When L0, M0, and hence for both electron M is equal to 0. But upward electron, that means clockwise, value plus half. Anti-clockwise, value minus half. Listen, value minus half, never plus half. S is equal to minus half. Clear? Listen, N is equal to 1, N is equal to 1, 1s, L 0, 0, M 0, 0, but S plus half, minus half, and hence all three quantum numbers are equal, but fourth quantum number, that is a spin quantum number, not equal. In second example, listen, 2p, and there are three electrons. So for all three electrons, N principal quantum number 2, N2, 2, 2. In p suborbit, L always 1 for all three electrons, L 1, 1, 1. Magnetic, minus 1, 0, plus 1. Magnetic, minus 1, 0, plus 1. And all are clockwise, and hence S plus half, plus half, plus half. Look at the board. Magnetic quantum number of all three electrons are different. And hence, it is clear, and according to Pauli principle, maximum three quantum numbers may be equal for two electrons of an atom. All four quantum numbers never equal. Now, conclusion of Pauli's principle. Conclusion of Pauli's principle. Look at board. An atomic orbital, listen, an atomic orbital can contain maximum two electrons. Listen, an atomic orbital can contain maximum two electrons with opposite spin. That is, an atomic orbital cannot contain three electrons, four electrons, maximum two. And an atomic orbital cannot contain two electrons in same spin. Maximum two with opposite spin. Listen, first 1, 2, correct. Second, in first clockwise, anti-clockwise, correct. In second, anti-clock, clock, correct. Two electrons in opposite spin, correct. But in third, clockwise, clockwise, wrong. According to Pauli principle, it is wrong. And anti-clock, wrong. According to Pauli principle, wrong. And this both A and B are correct and C and D are wrong. Clear? Next. Next topic is magnetic moment. And magnetic moment value gives nature of a species, either atom, ion. When an atom, all electrons paired, called diamagnetic. And when an atom or ion contains one or more than one unpaired, called paramagnetic. And nature of dia and paramagnetic also calculate from the value of magnetic moment. Topic is calculation of magnetic moment, and magnetic moment symbol mu is equal to n into n plus 2 root under n into n plus 2 bm. I am repeating, value of magnetic moment n plus n value of magnetic moment is equal to root under n into n plus 2 bm. Clear? Where n is number of unpaired electron, where n is equal to number of unpaired electron, and bm is unit of magnetic moment. Bm means Bohr magneton. Bm means Bohr magneton. It is unit of magnetic moment, and always keep in mind 1 bm is equal to 9.274 into 10 to the power minus 24. I am repeating, 1 bm value is equal to 9.274 into 10 to the power minus 24 joule per Tesla. Joule per Tesla. It is bm. 1 bm is equal to, again I am repeating, 9.274 into 10 to the power minus 24. Now, calculation of magnetic moment. Listen, when n is equal to 0, n 0 means unpaired 0. That means all electrons paired. All electrons paired. When all electrons are paired, the mu equal to n 0, 0 into 0 plus 2 bm, that means mu is equal to 0. And when mu is equal to 0, called diamagnetic. Mu 0 called diamagnetic. When magnetic moment value 0, called dia. Listen, magnetic value does not 0, called para. And when magnetic value increases, when magnetic moment value increases, paramagnetic nature increases. Look at board. When a number of unpaired 0, all are paired, mu equal to root under 0 into 0 plus 2 bm, mu is equal to 0, diamagnetic, and meaning of diamagnetic, repelled by external magnetic field. Listen carefully. Diamagnetic means the species which repelled by external magnetic field. Which repelled by external magnetic field called diamagnetic, and the species which attract by external magnetic field called paramagnetic. I am repeating. Diamagnetic means repelled by external magnetic field because all electrons paired. And paramagnetic means attract by external magnetic field. And when n does not equal to 0, that means when unpaired electron available, mu does not equal to 0, paramagnetic. For one MCQ, mu 0 diamagnetic, mu does not equal to 0, paramagnetic. Mu increases, paramagnetic nature increases, and paramagnetic means attract by external magnetic field, Listen, as number of unpaired electrons increases, when number of unpaired increases, paramagnetic nature increases, because when number of unpaired electron increases, value of magnetic moment increases. Clear? Listen carefully. In previous examination, I observed normally 6 types of question asked based on calculation of magnetic moment. When number of unpaired 1, number of unpaired 2, number of unpaired 3, number of unpaired 4, number of unpaired 5, and number of unpaired 6. In previous all examinations. Listen. Now, for number of unpaired is equal to 1. First, when n is equal to 1, n1 means when number of unpaired is equal to 1. When number of unpaired is equal to 1, value of magnetic moment root under 1 into 1 plus 2 bm, root under 3 bm, 2 plus 1 3 into 1 3, and value of root under 3 is 1.73. 1.73. Always keep in mind, when number of unpaired, both value of magnetic moment root under 3 and 1.73. 1.73. Always keep in mind both values. When number of unpaired 1, value of magnetic moment oral root under 3 bm, and value of root under 3 very simple 1.73. Now, when number of unpaired is equal to 2, when number of unpaired 2, magnetic moment root under 2 into 2 plus 2, 2 plus 2 4, 2 ja 8, and hence value of magnetic moment root under 8, and value of root 8 is equal to 2.82. Always keep in mind. For competition examination, listen, when n is equal to 2, magnetic moment root under 8, and value of root n 2.82 bm. Clear? Now, point number 3. When number of unpaired is equal to 3, when number of unpaired 3, value of magnetic moment, look at board, root under 3 into 3 plus 2. 3 into 3 plus 2, and hence 3 plus 2 5, 5 3 is 15, it will be root under 15 bm, and root 15 value is 3.87. 3.87. Always remember, always keep in mind, root under 15 value 3.87. Clear? I am repeating, when unpaired 1, root 3 bm, 1.73 bm, when unpaired 2, root under 8 bm, 2.82 bm, and when number of unpaired 3, root under 15 bm and 3.87 bm. Clear? Next. When unpaired is equal to 4, when unpaired is equal to 4, magnetic moment n into n plus 2, 4 plus 2 into 4, 6 into 4, 24, and magnetic moment is equal to root 24, and value of root 24 is equal to 4.89 bm. 4.89. Clear? And when n is equal to 5, magnetic moment root under n into n plus 2, 5 into 5 plus 2 bm, 5 plus 2 7, 5 is 35, mu is equal to root under 35 bm, and value of 35, 5.91 bm. Clear? Next, when n is equal to 6, mu is equal to 6 into 6 plus 2, and 6 plus 2 means 8, 8 6 is 48, value of magnetic moment root under 48, and value of root under 48 6.93, 6.9193, and it is value of magnetic moment for unpaired 1, unpaired 2, unpaired 3, unpaired 4, unpaired 5, and unpaired 6. And normally up to unpaired 6 and up to unpaired number of electron 6, already in previous year question asked. Clear? Now, some question based on calculation of magnetic moment. Calculate magnetic moment of chromium atom. Look at board. Chromium atom. We know that atomic number of chromium is 24. And atomic number means argon 4s1 and 3d5. It is electronic configuration of chromium. And look at board. Number of unpaired electron is 6. Number of unpaired is 6. And when number of unpaired electron is 6, magnetic moment is equal to root under n into n plus 2 bm. And hence, mu is equal to root under 6 into 6 plus 2 bm. Mu is equal to root under 48 bm. And always keep in mind, value of root under 48 is equal to, mu is equal to 6.91 bm. 6.91 bm. Clear? Next question. Calculate magnetic moment of zinc atom. Look at board. Zinc atomic number 30. Argon 4s2. Both are paired and 3d10. Listen, 3d10. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. Number of unpaired is equal to 0. That means all electrons paired, n is equal to 0, magnetic moment is equal to 0, and hence zinc is diamagnetic. Zinc is diamagnetic. Next question is calculate magnetic moment of magnets. We know that configuration of magnets. Argon 4s2 and both are paired 3d5 and all 5 according to Hund's rule. All 5 electrons will be filled one by one in same spin and hence number of unpaired is equal to 5 and magnetic moment is equal to 5 into 5 plus 2 bm and mu is equal to 5 to 7, 5 is 35 bm. And always keep in mind, value of root under 35 is equal to 5.91 bm. 5.91 bm. Clear? 5.91 bm. Clear? Next question. Calculate magnetic moment of iron plus and iron 3 plus. First, atomic number of iron 26, argon 4s 2 and 3d6 and 3d6 means electron filled first time one by one, second time in opposite spin, and hence in d6 there are 4 unpaired. But question is magnetic moment of iron plus. In case of iron plus, 2 electrons removed from iron atom and electron always removed from last orbit. And hence, when electron removed from 4s, iron plus has number of unpaired is equal to, it has 4 unpaired and magnetic moment is equal to root under 4 into 4 plus 2 bm. And it is equal to root under 24 bm. Clear? Next, in case, second question, iron 3 plus. In case of iron 3 plus, one more electron removed. And when one electron removed from 3d, then iron plus 3 plus has n is equal to 5. And when n is equal to 5, mu is equal to 5 into 5 plus 2 bm and it is equal to root under 35 bm. Yes or no? Next. Calculate magnetic moment of nickel plus plus. We know that nickel, atomic number 28, argon 4s2, 1, 2, 3d8, 1, 2, 3, 4, 5, 6, 7, 8. That means nickel has 2 unpaired, but in question nickel plus plus. Nickel plus plus, 2 electron remove, and electron always remove from last orbit. Electron always remove from last. 4s0 and 3d already 8. And hence 1, 2, 3, 4, 5, 6, 7, 8. There are 2 unpaired. And when unpaired is equal to 2, magnetic moment is equal to 2 into 2 plus 2 bm. And it is called root under 8 bm. Root under 8 means 2.82 bm. Clear? And it is calculation based on magnetic moment. Thank you very much.